Okay, so our second speaker is Joan Quirant from Ben Gurion University, and he's going to be telling us about massive spin-2 particles and the Swampland. So please go ahead, Joan, the floor is yours.
Okay, so let me start by thanking the organizers for inviting me to present my work. So I'm going to tell you about massive spin-2 particles and the Swampland. It's a work based in this paper that I did with Suman Kundu and Eran Paldi, plus some work in progress that has been unpublished. Okay, so let's start. Let me start by motivating the problem. So the first question one can ask is, okay, why do we care about massive spin-2 particles? So the point is that massive spin-2 particles always appears in string compactification, or generally, if we are working with theories with extra dimensions, we always have massive spin-2 particles. They are just the cycling copies of the graviton. So usually, when we work in string theory, there are two different pictures. Either there are no massive spin-2 particles in the spectrum, so we can have like scale separation, we can make the internal dimension to be very small, then we can like decouple all of them, we have something like this, where there are no massive spin-2 particles in the spectrum, or we have like this situation, if the internal and the external dimensions have the same length, then we cannot decouple them, so we have like an infinite tower of massive spin-2. So this is the usual top-down approach. But if we were effective field theorists and we were doing like effective field theory, we could ask, okay, but is there anything wrong if I try to do a theory with this just a single massive spin-2 particle? So is there anything wrong if I try to do a theory like effective field theory with gravity and maybe just one single massive spin-2 particle and like other stuff? Or maybe is there anything wrong if I do like massive gravity, so if I take the graviton to be massive? So is there anything wrong with these theories from a quantum gravity point of view? So we can be a little bit bold and ask, are these scenarios in the Swampland? Because they look like quite unnatural from a top-down approach. Or you want to be like more polite, we can ask, okay, what are the Swampland constraints for massive spin-2 particles? So these two questions, I'm going to try to answer them in my talk. So after this brief motivation, so this will be the content of my talk. I will tell you about the classical Regge Growth conjecture, in the case in which there is only one massive spin-2 particle in the spectrum, in the case with several massive spin-2 particles, this is the new part, and then some conclusions. And let me tell you that in all this talk, I will be always working in 4 dimensions, so always in D equal 4. Okay, so let me go with the mandatory slide of the Swampland. So I think I don't need to introduce the Swampland for this audience. We all know that not any effective field theory can be crystally coupled to quantum gravity. So you are familiar with the Swampland and you heard about massive spin-2 particles. Maybe the first idea that came to your mind is the massive spin-2 conjecture. So what was published by these people in this paper. The idea of this conjecture, what they did, is to apply the weak gravity conjecture to the ST1 mode of a massive spin-2 particle. So what they obtained is that if you have a effective field theory with a graviton and a massive spin-2 particle, then the cutoff of the theory scales like this. Well, this is the mass of the spin-2 particle. And if you are working with massive gravity, then the cutoff of the theory scales like the mass of the massive spin-2 particle. So I wanted to review this because in my talk, I'm not going to use it, but I'm going to kind of prove it. So what I'm going to use is the classical Regge Growth conjecture. So what is this about? Maybe you are less familiar with it. So it was formulated by these people in this paper. And technically, this is not a Swampland conjecture. Why? Because it should be true also without gravity. So it's like an experiment about effective theories in general. What it states is that the S matrix of a consistent classical theory cannot grow faster than S squared, a fixed and physical T. And this classical word here is important because what I mean is that I will be always working at 3-level scattering. So I will not considering loops or any kind of quantum correction, always like classical scatterings. So for instance, to give an example of what this means, because take any 2-2 scattering that you want, like the favorite 2-2 scattering. So then the contribution, because we are always doing things at the classical level, are the exchange diagrams and the contact diagrams, like any particle that can be in the propagator. So what this conjecture is telling you is that you take this limit, this has to be 0. So there cannot be an S growing like faster than S squared in the theory. So this is what is the tool we are going to use. So why should you believe this? So as the name indicates, it's a conjecture, can not be proven, but I'm going to give you 3 + 1 arguments in support of it. So first of all, is true in any two derivative theory for spin smaller than 2. So in any consistent theory that we have consistent. It's also true for classical string scattering amplitudes, and it's true for the X matrix, the A-string X matrix. Also, the second argument is that it can be argued in the impact parameter space. It can be like kind of proof. But there are some subtleties when going from this space to the usual STS space. One has to do like a transformation, and it's not clear that it works. And the third argument is that it can be connected with a chaos bound. So if one can show that if a theory in the bulk doesn't satisfy the CRG conjecture, then the dual, the CFT dual, doesn't satisfy the chaos bound. So the relation. And I have this extra argument, this plus one argument, is that non-perturbative gravitational scalar particles satisfies it. So why I'm calling it like plus one? Because this is for non-perturbative gravitational scattering. So this is not really a statement about the classical scattering, but non-perturbative. And it has been only proved for dimensions bigger than 4. Okay, so this being said, the idea is, okay, let's take this conjecture and let's apply it to theories containing a single massive spin-2 particle. So this is the main idea. This is the thing we want to do. So in other words, we want to see if it is possible to construct a theory where the scattering of the two scattering of identical massive spin-2 particle goes like this. This is what we want to do. Because we want to be like as general as possible, we will assume that this spin-2 particle can couple to anything, like to any particle with a spin smaller than 2. So it can be coupled to a massless spin-2, to a spin-1, or to a scalar particle. So we want to be as general as possible. So how do we do this? How do we construct this general scattering? So we will be doing a model-independent approach, meaning that I will not using any Lagrangian, but working directly with the amplitudes. So how we do construct the more general amplitude? Let me give you like the basic steps. So the first thing is, okay, we need to find all possible unshaped cubic vertices. So all possible cubic interactions between two identical massive spin-2 and other particles. So for instance, all cubic vertices between two identical massive spin-2 and itself, also two identical massive spin-2 and a graviton, a spin-1 and a scalar. So we need to find all the possible unshaped cubic interactions. This has been already done in literature, but so we need to consider all of them. The second step is, okay, we have the cubic terms, we also need all the quartic vertices, so all the contact terms. So we need to list all of them, and this will be like the most complicated thing, because I will show you that we need to consider a lot. I will explain it this later. So once we have the cubic and the quartic vertices, we can compute the most general amplitude. How? Just to construct the change diagrams, take two sets of cubic interactions, connect them to the corresponding propagator, so you have the change diagram, and multiply it by some arbitrary function. The principle can be whatever you want. So we construct, like, you see, like massive with a massive in the propagator, the same with a massless 2, with a spin-1, and with a scalar. And we multiply any of the diagram by some arbitrary function, and take also all the contact terms and multiply them by some arbitrary function. So for instance, let me do zoom in. So what this means is that I take in all like a set of cubic interactions that I found before, and I'm gluing them like with the propagator. I'm multiplying all this cubic by some arbitrary constant. So once I have this completely general amplitude, I take this limit. So I take the limit in which S is much bigger than T and expand the total amplitude. So we get something like this. So finally, in the result, I impose the CRG conjecture. So I impose that all these, if A3, A4, A5, whatever I obtain, if it goes with S bigger, with Sn to with n bigger than 3, it has to vanish. So I need to find a solution like for this such that all these things vanish. Of course, there is a trivial solution. Now you take all these constants to be 0, then you have nothing to do. So it's trivially satisfied. But the question is there any linear combinations of constants such that this amplitude can grow with S squared? This is the question we want to ask. So how many parameters are involved in all this problem? Let me give you like a list. So let me also tell you that I told you before that we want to be completely general. So we are considering parity even and parity odd interactions. So we are putting all of them into the game. So for instance, regarding massive spin-2 vertices, there are like 6 of them. With massive graviton, there are 9 of them. There are 4 massive 1, 4 with the scalar, and the contact terms. And the contact terms, I told you, this is like the trickiest part, because there can be many of them. So the idea is that you think about the contact terms, one can add more and more derivatives, so one can have more and more contact terms. So in this work, what we did is to consider contact terms with any but finite number of derivatives. So always like any number of derivatives but finite. And how do we put all these contact terms into the game? So there is an algorithm developed in this series of papers. I will not explain it to do it, how to do it. You can go to the paper. But to have an idea of how many parameters are here, so we had to construct like 201 different contact structures and then multiply them by some arbitrary function. So it was really a nightmare, right, to put all these contact terms into the game. So okay, this being said, what is the result? So what do we get? Is a theory like satisfy the CRG conjecture, is not a theory. So the question is, this is the main result of this first part of the talk, is that to satisfy the CRG conjecture, all cubic vertices must vanish. In other words, the theory is trivial, so there is no such a theory. Or you want, I can put it like this. So if the CRG conjecture holds, is true, a theory containing a single massive spin-2 particle will be inconsistent. So a single, I mean, there's only one massive spin-2 but can interact with other particles. And I'm not considering a particle with spin higher than 2. So this is the main result of this first part. So in other words, these two pictures I showed you at the beginning, so a theory in which there is some particles and a single massive spin-2 in the spectrum, or a theory of massive gravity will be in the Swampland if the CRG conjecture is consistent. So this is the first and the main result of this first part of the talk. So, okay, once I show you the result, the natural question is, okay, what about several massive spin-2 particles? So it could be that maybe I add an extra massive spin-2 particle and then it solves the problem. So is this the solution? Maybe not. Maybe the only possibility is that I have an infinite number of massive spin-2 particles. For sure, we know this should be true because this is just a closed-lane compactification. So how is the CRG satisfied in this picture? So what is going on if I put several massive spin-2 particles? So let me explain you how we should modify what we did to include several massive spin-2 particles. So the idea is simple. Take the general case, or take the case before with all the cubic interaction, all the contact terms, and add an extra cubic interaction. So add the interaction between two identical massive spin-2 particles and other massive spin-2 particle with any mass. So I'm showing you here, for example, this kind of vertices. There are 7 parity-given operators. So one can think, okay, not that complicated, no, because it's just all the parameters we had before plus 7 extra new constants. But this is not the end of the story because we want to be general. We want to add not only one, but like any massive spin-2 particle can be in the propagator. So we can couple these two identical massive spin-2 to any other massive spin-2 particle. So you see that now we have to add sum over like all infinite possibilities. So this is quite complicated. So now the situation with any number of massive spin-2 particles will be like this. So this is the same problem we had before, plus this list of in principle infinite new constants. So the situation gets like very, very, very involved. So what we thought is, okay, let's do it simple. Let's do a theory, let's take a theory that we know very well, and let's see what we can learn. So what we did is let's do a proof of concept. So let's take general relativity, a theory that we know is consistent, and put in and compactify this theory. So I compactify into 4D, and I'm just asking for the internal dimension to be like closed, compact, and Ricci flat. Ricci flat because I need to solve the equation of the Ricci of the Einstein Lagrangian internal dimension. So this is the only thing I'm demanding on internal dimension, on internal dimensions. So why is this case interesting? So first of all, notice that in the, let's say, parent theory, so in the theory we start with, this is just pure gravity, and pure gravity. I told you that the CRG conjecture is satisfied in pure gravity. So we know that in the setup, the CRG conjecture should be satisfied. But the point is that when I go to 4D, and this dimensional reduction was already done in the literature, so we had to like we didn't have to take it from the literature. So the point is that when I go to 4D, I have a theory of a graviton, and then because I'm reducing the graviton and the internal dimensions, I have also massive spin-2, spin-1, and scalar particles. I will have something like this. I have the graviton, but like massive spin-2 particles, and you see like coupling, like interaction between the massive spin-2, the scalars, and the spin-1 that come from the dimensional reduction of the graviton in the parent theory. And the idea here is that all these couplings here, there are no degrees of freedom because they are just come from you started with a theory where there are no like any constant, you stay with gravity, you compactify and you get interactions. So they are completely fixed by the internal geometry and they are related. There are some related among them that I will not show. So this is the theory we want to work with, the general relativity and compactifying 4D. So the idea is, okay, let's repeat the same game. So let's take the theory we have in 4D, that is a theory of interacting massive spin-2 particles, and compute a scattering of two identical massive spin-2 particles, two massive spin-2 of this infinite tower, and impose that this scattering grows like S squared. So what do we get? What constraints do we get? So what we get is constraints on the spectrum of the theory. So this is the main result of the second part. So this is what we get. So what this means. So notice that this should be true for any edge because I can do this scattering with any two massive spin-2 particles in the tower. So these contributions come from the scattering from the exchange diagrams of two massive spin-2 particles exchanging a third massive spin-2 particle. So you see that we are summing over all the different massive spin-2 particles. It's not always the different. And what it is coming here is just take the graviton in the parent theory, just do the usual standard thing, like put it like in terms of the given function of the Laplacian, and then this coming here comes from the triple overlap integrals, and so I can have like contact terms come from the quartic overlap integral. So this contribution, and these other contributions come from the change of graviton and the same massive spin-2 and contact term. So this is the main result. Okay, what can we learn from this equation? There are two very interesting things I would say. First of all, we see that because this term is positive definite, there has to be some negative term here to compensate this to obtain a zero. So what this means is that because this has to be true for any massive spin-2 particle in the spectrum, so and this we need a negative contribution. What one can derive from this is that for any massive spin-2 particle in the spectrum, there has to be another massive spin-2 particle whose mass is bigger than this mass. In other words, say that I do this scattering for the smallest massive spin-2 particles, so for M1. Then what this equation is telling me is that I need M2 whose mass is bigger than M1, and then I do the scattering for M2. Then what this is telling me that I need M3 bigger than M2, and I can do it again and again. So what this is telling me that I need an infinite amount of massive spin-2 particles in the spectrum. And the second thing that I can learn from this, so because this is positive definite, it has to be negative, but it cannot be too negative. Otherwise, I cannot compensate this. So what it's telling me is that there is a bound on the maximum allowed gap. So in other words, I cannot take a massive spin-2 particle, another massive spin-2 particle, and make the gap between the masses arbitrarily large. It's not allowed. This is this bound between the masses of two arbitrary spin-2 particles in the spectrum. Where this, I mean, one can use this and derive this bound. So what we learn for this from this example is two things. So first of all, the CRG and the dimensional reduction applied to general relativity as a model is that it has to be like can be like either there are no massive spin-2 particles in the spectrum or there are an infinite tower. So in other words, it is like forbidden to couple a finite number of particles. So this cannot be made consistent with the CRG conjecture, like never. And also, let me point out that this bound we are getting here, it already appeared in the literature in this old paper where they were studying like gauge invariance, were truncating the tower, and also in this same paper we use, they derive not only this but stronger bounds using unitarity. But it's nice that we can recover the same bounds like using the CRG conjecture. So with this, let me just go to this was short, okay. So the conclusions and to the outlook. So the take-home message, the main result of one of the main results of this talk is that if the CRG conjecture holds, an effective field theory containing just a single massive spin-2 particle and no higher spin-2 particles will be in the Swampland because it cannot be. So as a theory of just a single massive spin-2 particles cannot be made consistent with the CRG conjecture. This is one of the main results of this talk. The second result is that what if we add several massive spin-2 particles in the game? So the general case is very, very hard to deal with, but we can do like a proof of concept taking general relativity and doing a dimensional reduction of this theory. What we learned is that, first of all, we need an infinite number of massive spin-2 particles. We cannot truncate the spectrum. And second, that there cannot be parametric gaps between the masses of the spin-2 particles. There's a bound on the maximum gap. So this is these two pictures, this is what I told you before. So a theory of just massive gravity, theory in which there is just one graviton and a finite number of massive spin-2 particles will be inconsistent and invisible if the CHG conjecture is true. So that this is okay. This result is doing with the relative with the we obtained it using just general relativity, but I mean we expect that it's true in the general case. So of course, future direction is to have like a proof of the CRG conjecture, or to have like a more direct evidences of it, and also to apply it to other content, because you see that the CRG conjecture can be very powerful to derive constraints on consistency of particular theories. So this is all. So stay tuned, because I think we will publish some this second paper on the several massive spin-2 particles. So that's all. So thank you. If you have questions or comments or complaints or whatever, so I'm open to it.
Okay, great. Thanks a lot, Joan, for the great talk. Any questions? You can just like unmute yourself and go ahead. Alvaro?
We had a question too.
Oh, maybe Chicago go first then.
So just to make sure we understand the assumptions going into this. So were you excluding other particles, or doesn't matter what the other particle content is beyond the mass of spin-2?
What do you mean? So we are assuming that in the spectrum there is like any particle with spin is lower than 2. I mean, we are not assuming anything about the spectrum rather than that.
Sorry, so you say it again. So you're assuming there are. You could have
we're assuming that in the spectrum can be like a massive spin-2 particle, and then it can be any other particle with a spin smaller than 2. So this is the only assumption we are doing. We are not assuming anything else about the other particles. They can be whatever you want, as far as they have a spin lower than 2, but they cannot solve the problem. That's the result.
So just make sure we understand the dimensional reduction case. If you just dimensionally reduce whatever 5D to 4D on the circle, and you move your lambda effective down, so you're just above the mass of the first massive spin-2, integrate everything else out. Is that inconsistent?
Yes. You cannot. Yes, exactly. You cannot have just one massive spin-2 particle. Either you have the full tower, or you don't have any spin-2 particle in the spectrum. But you cannot, like, yes, I just said, like, just integrate all of them except one. That would be inconsistent with the CRG conjecture. That's the point.
No, but forget the CRG conjecture. Suppose I just do it. Why is it inconsistent to do it? Don't I get a consistent theory? I start with a consistent theory, and I integrate out everything except the first massive spin.
Okay, the point is that the CRG. Okay, I see the point. So the point is that if you do that, then the CRG conjecture is violated. So in other words, I can construct a scattering in which the amplitude goes like s to the q or faster, and we think that kind of theories could be inconsistent. That's the point.
But I'm starting with a consistent theory, say in 5D. I got consistent classical scattering. I just integrate everything out. What I get must be consistent, no?
Yeah, no. I mean, that's the point, that you cannot do it. I mean, you cannot, because no. I mean, the point is that because the how the theory is, there is no way in which you can like decouple all the particles except from one. That's the point, because there is this bound between the masses of the spin-2. So there is no way in which you can decouple, like you can have a theory with only one massive spin-2 particle in the spectrum and all of them decouple. I mean, there is no way in which you can do that. That's the point.
Okay, thank you.
And I had a question as well. Just quick, I don't know. Do you have a comment on whether there's any applications to the dark dimension scenario?
Ooh. I don't know. We haven't thought about that. But it shouldn't be. You know, I don't have much to say. To be honest, I haven't thought about that.
Right, Alvaro, I think you were first.
Yeah, my mic was not working, so I'm trying from a different mic now.
Oh, I see. Sorry.
I mean, I have a very basic question, which is there any, like, from these arguments or from any general Swampland arguments, is there any way to rule out one extra one extra spin-2 particle, which is massless?
What has been? You mean two gravitons? Something like two gravitons?
Yeah, I mean, we know this doesn't happen in string theory or anything, but I have no idea if this can actually be ruled out from this kind of bottom-up argument or anything like that. Is that known, or
Let's see.
do you know from this?
I don't think we have looked at that. I mean, yeah, in principle, yeah, you can. I mean, we didn't look at that theory with two gravitons, but in principle, one could look at that. Yeah, I don't see. Yeah, I mean, we can do the same. Like we can do all this game of having like two gravitons and do the game. But I don't know. I mean, I think we have not thought about that. So I cannot tell you anything. But in principle, yes, in principle, we should be able to derive constraints on that kind of theory. Yes, with two gravitons.
Thank you.
And Vincent.
Yeah, I had a question about the infinite tower. So, is it correct that you only consider an infinite tower of spin-2 particles? And if so, I was wondering that, yeah, if you do compactifications, typically you have also other towers as well. And I was wondering what would happen if you also include those, whether they would mix, whether
Yeah.
additional
question, no.
interactions, and that would alter the results.
Yeah, no, good question. No, actually, okay, I didn't say it, maybe I didn't explain it well, but we are not considering just one massive spin-2 particle, but any number of massive spin-2 or scalars, like the number of particles with spin smaller than 2, they can be infinite. We are taking that into account. Yeah, the number of particles with a spin smaller than 2, it doesn't change anything. But yeah, we are actually considering like a tower of spin-1 scalars in the game. Yes.
Okay.
All right. If there are no other questions, I think we can go ahead and thank Joan another time and Stefano as well for the great talks. And now I'll end the recording.